Okay, so non-free fall. Non-free fall means you have to consider the effect of the air. When an object falls down through the air, it experiences an upward air resistance. That's the new effect, is when something moves down through the air, it's actually colliding with the air on the way down and feels a resistance from the collisions, here labeled R, the air resistance force. It's directed upwards when an object moves down. Now, if you throw a ball upwards, then it's moving up through the air and it would feel a downward air resistance. Of course, it also experiences a downward force of gravity, a downward gravitational force, also known as the weight of the object, which is just the object's mass multiplied by g. It's not that air resistance affects the weight of a thing. A feather weighs just as much as when it falls. It's just that the air resistance is a force that is in opposition to the weight. Picture might help. Here's a piece of paper falling through the air. The paper, as it drops, actually collides with the air molecules, and those collisions help support the paper as it falls. Now, the rock hits the same air molecules, but the rock weighs so much that the little force of those collisions doesn't have much effect. Like ants can pick up a grasshopper, but ants aren't going to have much effect on you. The collisions of little tiny air molecules aren't going to affect the falling rock very much. They hit the rock just as hard, but it doesn't have much of an effect on the rock's motion. Compared to what you see in a vacuum, no air at all, they both fall exactly together. And we've learned all about that. So the air resistance, it's all from the collisions with the air molecules. It's going to, as it moves down, it's going to strike the particles, and that causes an upward force on a falling object. So let's see the effect this has. Suppose you have a 20 Newton falling object. It encounters 5 newtons of air resistance. What is its acceleration of fall? Okay, so it's a word problem. We need to solve for the acceleration of the falling object. How do we find acceleration? Well, is this a kinematics problem where I know the change in velocity and I figure out the acceleration from that? No. Here I'm given forces. And because I know the forces that act on the object, I can find the acceleration using Newton's second law, where I take the net force that acts on the object and divide it by the object's mass. So I need to find two things. First, the net force on the object. So here's the falling object. It weighs 20 newtons. That's the weight. So in other words, mg is given to be 20 newtons, about 5 pounds. And it encounters 5 newtons of air resistance, roughly a pound of air resistance. That's R. And we're told it's 5 newtons. What is the net amount of force that acts on the object? Well, 20 minus 5, right? They're in opposition to each other. So I would do a subtraction to get the acceleration. 20 newtons minus 5 newtons. You might say, you know what, I want to call up positive, and I would say it's 5 minus 20, and then you'd have minus 15 instead. That's totally fine. It's your choice whether you want to call up positive or down positive. Now, that's the net force, 15, or if you flip things, minus 15. What is the mass of the object? Is the mass 20 newtons? No, that's the weight. Remember, weight and mass are different. To find the mass, you see mg is equal to 20 newtons. That tells me what the mass is. The mass is 20 newtons divided by g. right? See how I rearranged it to find what the mass is. And G is about 10, so 20 over 10 gives me 2 kilograms. Mass has nothing to do with gravity. I mean, things have mass even if there's no gravity around. So the mass of this 20 Newton thing is about 2 kilograms. So that's 15 over 2 gives me 7.5. And what are the units? What am I measuring here? This is 7.5 meters per second squared of acceleration. And that's sure less than G. And I knew it had to be less than G because the only way something's going to fall at the rate of G is if the only force on it is its weight. The only way that something falls at 9.8 meters per second squared is if there's no air resistance. If the only force that acts on it is gravity, is mg. In this case, there's a little bit of subtraction from the air resistance that reduces the net force from 20 down to 15. So of course, the acceleration is going to be smaller than 9.8 or less than g. So non-free fall occurs, so whenever a homework problem, exam question mentions anything about something moving through air, it's going to be non-free fall. So it occurs when air resistance is factored in. If I drop a feather, I have to factor in air resistance to understand what's going to happen. If I drop a bowling ball, then the bowling ball is not affected much by the air resistance. And I'll explain, I'll draw that out to explain. But from experience, bowling balls are going to fall pretty much like free fall, whereas feathers and paper just drift down to the ground. So what factors do affect air drag? In other words, if you have an object, what controls how much air resistance it's going to feel? Depends on two things. One is the object's speed. And you know about this. If you put your hand out a car window, the faster the car is going, the more you feel that air blowing back against your hand. That's air resistance, air drag. So faster a thing moves through the air, the more air drag or air resistance it feels. Also, it depends on the profile area. And you know about that too. If I open my hand like this, I'll feel a bunch of air resistance as the car is driving. If I put my hand like this, then I don't feel as much air resistance. The profile area affects how much air drag there is, which it all makes sense because remember, it's from collisions with the air. If you make yourself narrow, not much collisions. Most of the air misses your hand and very little air drag. Okay, so because of this air drag, heavier objects in air actually fall faster. And this is the thing that just threw off Aristotle and everybody else for thousands of years. You see, they didn't realize that there was a force of air resistance. They thought that heavier things fall faster because, that's the natural thing for them to do. They have more mass to them, and therefore they're going to fall faster. Really, the natural thing for all things to do is to fall the same rate. Okay, so let's explain what's going on here. Suppose you have a little feather. The feather has a very tiny weight. When it encounters air resistance, R, notice how the net force is greatly reduced by the presence of that air resistance. Okay? Because the weight is so little. Like if the weight is 1 Newton and the air resistance is half a Newton, that's a big effect. Okay? But compare that to a heavy ball, like a rock that falls through the air, bunch of mass. Now it has a tremendous weight. and it's going to encounter some air resistance when it drops. Maybe the same amount of air resistance as the feather. But you know, what's half a Newton to something that weighs 100 newtons? It just barely affects the net force. So in other words, on a heavy object, the net force is just it's actually equal to mg minus that air resistance. But you know what? Air resistance on it is just so much smaller than the weight that you might as well just kind of ignore it. And it's approximately just equal to the weight. What's 100 newtons minus half a Newton? And almost 100, right? So that's why heavier things will actually fall faster. That's why if you, on the Earth, drop a hammer and a feather, the feather loses big time. But on the moon, they fall together. No air resistance to get in the way of the falling object. Something special happens when you fall through the air. You might have heard of terminal velocity before. Terminal velocity is when the object's moving fast enough that the air resistance becomes just as big as the weight. Remember, with air resistance, the faster it goes, the bigger the air resistance becomes. The air resistance builds up as the speed increases. So it can go fast enough so that the air resistance is actually matching the weight. Now, what about the net force? Hey, if the air resistance exactly balances the weight, now the net force is 0 newtons. And then what about the acceleration? If there's no force on an object, what is its acceleration? 0 meters per second squared of acceleration. And what about the velocity? Does 0 acceleration mean 0 velocity? No way. 0 acceleration just means there's no change in velocity. Remember that? Acceleration's not, something with big acceleration doesn't mean it's a high speed. You know, the moment you slam on the gas, you still haven't moved yet. But 0 acceleration doesn't mean 0 velocity. It means the velocity is not changing. In other words, the velocity is constant. Or we say the velocity has been terminated. Or it's reached a terminal, final velocity. It's no longer gaining speed. It's reached the maximum speed it's going to have when it falls to the Earth. An animation might help. As the object goes through the air, as it goes faster and faster, it's hitting the particles in the air at a higher and higher rate, and that's why the air resistance gets bigger. So when something falls through the air, it hits more and more air the faster it goes, and the air drag, here called F air, gets bigger and bigger and bigger the faster it goes. Notice how the faster, as it goes faster and faster, the net force becomes smaller and smaller and smaller. Not because it weighs less, that's crazy, it doesn't weigh any different. It's just that the net amount approaches 0. And when the net force goes to 0, now the acceleration is 0, and it reaches a constant speed as it drops through the air. This is what happens when it rains. When a raindrop falls, it gains speed for a little while, but then it just drifts down to the ground. If you've ever watched drizzle in a streetlight, the drizzle just floats down to the ground. It's because the air drag is just as big as the weight of the droplet. This is a good thing. Otherwise, raindrops would be hitting us like bullets when they come down from the cloud. They don't go that fast. They just drift because they've reached terminal velocity. Okay, some questions. If a 50 Newton rock is to fall at terminal speed, what is the air resistance needed? Pause it, work it out. Okay, welcome back. It weighs 50 newtons. When we say a 50 Newton rock, that means the weight is 50 newtons. If it's going to fall at terminal speed, that means the net force has got to be 0 on it, so that the acceleration is 0 and it's no longer gaining speed anymore. So that means that this rock that weighs 50 newtons, mg is equal to 50, it's got to have just as much air resistance on it. The air resistance also has to be exactly 50 newtons, so that the net is equal to 0. Okay. As a skydiver, a skydiver reaches terminal velocity. They don't fall at the rate of g. They reach a peak speed when the air is blowing back against them just as hard as they weigh, and then they're just drifting down. As a skydiver falls faster and faster through the air, what happens to the air resistance? It gets bigger and bigger. We just talked about that. Faster and faster means more and more collisions with the air particles and more air resistance. What about the net force? As she falls faster and faster, what happens to the net force upon her? It actually decreases. Careful, it's possible to get tripped up here. Just because the air resistance is getting bigger, that doesn't mean the net force is bigger. In fact, the net force gets less and less because there's the weight being opposed by the air resistance. So the air resistance gets smaller and smaller. As she falls faster and faster, what about her acceleration? Is it getting bigger? Not at all. In fact, as she goes faster and faster, remember the net force on her is getting smaller and smaller. So her acceleration is absolutely getting less and less. Just because something's gaining speed doesn't mean that its acceleration is getting bigger. In fact, she's gaining speed as she falls, but the rate at which she's gaining speed is getting less and less and less. The moment she jumps out of the plane, she accelerates at g. But as she reaches terminal velocity, she's going faster and faster, but not at g, not at the rate of g. It gets to a point where her acceleration is actually zero. Just remember, the net force goes to zero. Therefore, the acceleration she has is getting smaller and smaller up to the point where it actually reaches no acceleration at all. And that's the terminal velocity. Some typical terminal speeds. A skydiver is going to reach a terminal speed of about 130 miles per hour. A baseball's terminal speed is less than 100 miles per hour. That just means if you were to drop a baseball, it would never get faster than about 96 miles per hour. Doesn't mean you can't throw a ball greater than 96. Pitchers can throw a 100 mile per hour fastball. It just means that the air drag is going to slow it down. Raindrops, fortunately, only get up to 20 miles per hour. If they were free falling all the way onto your head, you'd have to go to the hospital when it rains. Okay, when we talk in person, we'll do some of these brain teaser type questions.